Section 6.2 is on parallelograms. The definition of a parallelogram is a quadrilateral, that is, a four-sided polygon that has both pairs of opposite sides parallel. So here we have parallelogram ABCD, and we designate it this way with a little parallelogram, kind of like we did with triangles, and then the letters of the vertices, A, B, C, and D. The order here doesn't matter, but you do need to, doesn't matter where you start, but you do need to go around as you go around. So A, B, C, D. I could have started at D and gone backwards, D, C, B, A. What you can't do is go across. I can't talk about A, C, D, B. So name the four vertices in any order, starting with any one, but just make sure you go around. So for the definition of a parallelogram, sides AD and BC need to be parallel to each other, and AB is parallel to CD. So that's the definition of a parallelogram. Now, given that that's what a parallelogram is, there are several theorems that apply. So I've gone ahead and sketched our little parallelogram up here so we can refer to this. The first theorem says that opposite sides of a parallelogram are congruent. Remember, definition is that opposite sides are parallel, but the first theorem says that opposite sides are congruent to each other. So we can go ahead and put those marks in there. AD is congruent to BC, and AB is congruent to DC. Theorem number 2, opposite angles of a parallelogram are congruent. So those that are across from each other. So angle D is congruent to angle B, and angle A is congruent to angle C. Theorem number 3, consecutive angles in a parallelogram are supplementary. In other words, angles that are next to each other. So angle A and angle B are supplementary. They add up to 180. Angles B and C are supplementary. They add up to 180. Angles C and D are supplementary. They add up to 180. And angles A and D are supplementary. Theorem number 4. If a parallelogram has one right angle, then it has four right angles. Now, it might seem kind of strange looking at this picture. None of those look like right angles. But remember, the definition of a parallelogram is both pairs of opposite sides are congruent. So technically, a rectangle is a parallelogram, which we'll talk about in more detail in an upcoming section. But if one of these angles is a right angle, then all four of those have to be right angles, because opposite angles would have to be congruent, and consecutive angles would have to be supplementary. Theorem number 5. The diagonals of a parallelogram bisect each other. So when I draw these diagonals, BD and AC, they're not congruent to each other, but they do cut each other in half. So M is actually going to be the midpoint of both AC and BD. So segment AM is congruent to segment MC. Segment BM is congruent to segment MD. And theorem number 6, a diagonal separates a parallelogram into two congruent triangles. So in this case, I just drew diagonal BD. So triangle ABD is congruent to triangle CDB. And we could actually prove that using one of the theorems that we used back in Chapter 4. But we're not going to take the time to prove that now. So make sure that you're familiar with all 6 of those parallelogram theorems. Now let's put them to practice in a couple examples here. Here we have parallelogram ABCD, and we need to find the values of x, y, and z. Well, first of all, I notice that AB is 4x, and I know that AB is congruent to DC because opposite sides of a parallelogram are congruent. So 4x equals 18. X is equal to 18 over 4, which reduces to 4.5. Next, let's see. So I have a diagonal AC here, and I know that the diagonals of a parallelogram bisect each other. So M is actually the midpoint of AC. So I know that AM is congruent to MC. So I can write an equation with that. 7y plus 3 equals 8y, and subtracting 7y from both sides, y is equal to 3. And for my last one here, I need to look and find z. Z is up here, so the measure of angle ABD is 2Z. And I'm also noticing that since AB is parallel to DC, AB parallel to DC, then this diagonal BD is actually a transversal that creates alternate interior angles. So 2Z is congruent to 18 because they're alternate interior angles formed by a transversal cutting through two parallel lines. So 2Z is equal to 18 and Z equals 9. And let's take a look at our last example here. This says find the coordinates of the intersection of the diagonals of parallelogram ABCD given the coordinates of A, B, C, and D. Now remember that the diagonals of a parallelogram bisect each other, so M is actually the midpoint of AC and of BD. So what I would need to do is use the midpoint formula. So the coordinates of M are going to be -3 plus 5 over 2 and 0 plus 4 over 2, or 2 over 2 and 4 over 2, or 1 comma 2. I could check that and do the same thing. In this case I used A and C. I could do the same thing with B and D and make sure it's the same. But that's the coordinates of the intersection of the diagonals of this parallelogram. And actually, if you have this formula in your calculator, which I would, or this program in your calculator, the midpoint program, I would strongly recommend you do that, because in future sections we're going to be doing a lot with midpoint, slope, and distance. So the coordinates of the intersection of the diagonal are 1 comma 2.